Today, we're going to be working on modeling functions and applications. And we're going to focus on modeling through regression, which is a major part of the AP Pre-Cal curriculum. We're going to use mostly the TI-84 to do that, so that's one I'm going to be using to model up here. So I've got the steps first for building regression models on the graphing calculator. It tells you to enter the data into the stat form. And so we've got some of the printouts here. Stat on the calculator is right here, and I'll go ahead and show it to you on my calculator as well. Stat is right off to the arrow keys right here. So we hit stat, and then we're going to hit edit right there so that we can get our tables here. And I've got a bunch of stuff in here, so I'm going to clear my tables. There's my tables. L1 is going to be what we represent X with, and L2 will be what we represent Y with. As we go down here, it tells us we are then going to use stat to calculate equations. So it says in the stat menu, arrow over to calculate. So once we have our data in there, we would go stat and then move over to calculate. And so our calculator does the linear regression with AX plus B. It does quadratic regression, cubic regression, quartic regression, the linear regression with A plus BX. Usually that's used in AP Stat, but either one of those will get you the correct answer. Then that's the natural log regression, exponential regression, power regression, logistic regression, and then the sign regression. Those are all the ones, you'll see a lot of those in pre-cal, most of them, in fact. Today, we're going to stick to the polynomial ones. So the linear, the quadratic, the cubic, and the quartic ones are the ones that we're going to stick to in this unit 1. All right, once you have the data in there and you've calculated whichever one you have chosen, you're going to get a menu that looks like this right here. And I've chosen cubic regression for the picture. It says the X list is L1 and the Y list is L2. Then right here where it says store regression equation, we hit alpha trace to get this Y1 on there. What that does is it will write the equation for you on the main screen, but it will also store it in Y1 so that you can use it to calculate other equations. And then calculate is what you're going to hit at the bottom there. All right, so there's a table up here on the top, and we're going to go ahead and use that one for our first example. It says it's the age in weeks and then the weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are on this table. So here we go. We're going to hit stat, and so that's this button right here, and then we're going to hit edit. In L1, I'm going to put in my t values. And so there's that, 4, 5, 6, 8, and 12. And then in L2, I'm going to go ahead and put my weight. I verify that they're all lined up and that they're correct. If you leave one out, you're going to get an error. And then if you leave something else, if you mistype or something, it's going to give you the wrong information. So you want to make sure that it looks exactly like the one on your paper here. All right, it does tell us to go ahead and do a linear regression of that. Can be used to model this data. In some cases, you're going to have to figure that out yourself. Remember, we've done the differences, so we can see that our differences here are linear. You can check to see if they're quadratic, if they're cubic, and all the stuff that we've done to predict the equations. But for this one, it's linear, so I'm going to go stat, calc, and then I'm going to go to my linear equation. Since it tells us to use the A to plus bx, we can use that one. But again, both of these are the same thing. It's just the format that it's going to give it to you in. And so it says my X is L1 and my Y is L2, and that's correct. That's the way I put the data in. And then when I go here to store regression, this is where we hit alpha. So I'm going to hit the alpha key here and trace. And that gives me the Y1. And then I'm going to hit calculate. And so here's my equation. For the AP Pre-Cal test, you are going to want to use 3 decimal values. So make sure when you write this equation, you write it with the 3 decimal values for the test. So here's my equation. Y equals, the A value was 3.545 plus my slope of 0.185x. So we went ahead and did all of this. We got the same information that they just got there just so that you could see it. Oh, and there was a space to write it here, so I'll rewrite it in the correct location. So there we go. Now, it says using the linear model from part A, what is the predicted weight in kilograms of a baby that is 10 weeks old? So I want to show you how to do that on there. Since we went ahead and stored our equation, and 10 weeks old, that is the T. So T is equal to 10 is what it's telling me. And so I can actually use the function notation with the calculator. I can hit alpha trace to get that Y1 on this main screen, and then do the 10, and it will do the math for me. Again, 3 decimals is what we're going to want to keep, and so that is 5.395 kilograms, because that's going to be the weight at 10 weeks. So the weight, now it says the weight of a 6 baby is 5.3 kilograms. Using the model from part A, what is the age in weeks of this baby? And so this is working backwards. And so you do have a couple of ways that you can do this. Since we stored our equation in Y1, I can hit second graph, and I can go to my table here, and I can look at my data points, and I can try and find that 5.3. That's pretty close right there at the 5.395, but it's not exact. We can go ahead and put this 5.3 that it's asking about right here. 5.3 is equal to 3.545 plus 0.185 x, and we can solve for that x. Since we have this equation in my y1, I can also put 5.3 in my y2, and I can find the intersection of those two because that would tell me that part. So I hit second trace intersect, enter, 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 and there it is at 9.486. So T would be equal to 9.486 weeks, since we're looking for the T value. So we can use the calculator quite a bit here, but you're modeling the information on a data, and then you're using it to predict information. All right. On the bottom here, you've got a little tip on what to use. While some problems will indicate which model should be used, you will also be expected to select an appropriate model type based on a given table of values or by the context of the problem. So last class we talked about that the context can tell you which type of problem you're looking for. If we're talking about an area problem, well, you know that's a quadratic. If we're talking about volume, that's a cubic. So you're going to want to look at things like that. In linear models, you've got that constant rate of change. Now it says roughly here because since this is real life data, it sometimes will not come up to the exact value, but if it's just off by a little bit, then you know that's linear data. Or graphing that stat plot and seeing to see if it makes a linear equation. For a quadratic model, it's roughly linear rates of change, or roughly symmetric with a single maximum or minimum context involving area. All right, so here's an example of a problem, and we're going to determine. It says balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. In that case, it's saying radius measured to the amount of water it's holding. There we go with volume. So this would be cubic because volume is measured by a cubic function. All right, here's some more examples. Totino's pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 and $2.19, depending on the variety. The total number of Totino's pizzas are counted relative to the total price of the purchase. In this case, that would be linear because these prices probably depend on 1 topping, 2 topping, and 3 topping, and so on. So we're looking at something that's growing linear. A sprinkler is placed in a yard to water the grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler. Area, again, that's quadratic. We know that from geometry that area is quadratic, so we would want to do a quadratic regression for that. So that's what we're looking at in context of the problems, really thinking through what is it talking about and what kind of function would best model that. All right, so here we've got one that shows us a table of values again, and it's asking us which function best models the data. We can look at our differences to see if our differences are constant for linear, if our second differences are constant for quadratic, or if the average rate of change is linear, or cubic, and so on. So we know it's going to be either linear, quadratic, or cubic by this equation. Now, when I look at this data here, I see it is going from 5 to 10.6 to 15.4 to 17.1. So these differences are getting closer together. Then it hits 18 and then goes back to 16 and a half, 10.2, and then 2.8. Well, we know this U shape or parabola shape is called a quadratic. So this is going to be best be modeled by a quadratic. This being the center, and then we can see the symmetry on both sides. So on 18, it was right here, and then we can see it's not exact. Again, it's real life data, so we're looking at it close to, but these two are basically symmetrical, these two, and then these two, the farthest two out here, because the differences here are different than the differences on this side, so you have to keep that in mind as well. So this would be a quadratic one. So when we write the equation here, we're going to we'll practice another one just so that you can see it. I'm going to clear what I have in my calculator. When you hit stat edit, my information's there from the last table. So I'm going to go over to the L1 and hit clear and then enter, and that clears the data completely. You don't want to hit delete because then you'll delete the column name, so the L1 and the L2. All right, so you're going to put the X values in L1 and the Y values in L2. Go ahead and do that. All right, so now we have all of our data in there, and we know this one is a quadratic. So I verify that this data is correct. You do not want to make a typo error that's going to cause the entire equation to be off in all of your calculations. So make sure you check those carefully. Then we hit stat and calc, and the quadratic one is over here, quadratic regression. So that's the one that I'm going to want to hit. Again, my X is L1, my Y's are L2, and then I'm going to go over to this store regression equation, and I'm going to hit alpha trace and put my Y1 there. This now gives me my equation. And again, I want to make sure that I have 3 decimal values when I write that down. And so I got negative 4.883x squared plus 15.958x plus 4.996. So there's our equation. That's the one that we would want to use in order to predict information. All right, speaking of predicting information and verifying that things are correct, it tells us here that the next part is residuals that we'll talk about. When we use a model to predict values, we expect our model to produce values reasonably close to the actual values, but our models are not expected to result in exact values generally. The difference between an actual value and the value predicted by a model is called the residual. And so here it is, the residual is equal to the actual value minus the predicted value. All right, so we're going to look at that and see what that interprets with our data. So again, we put this into our calculator using the stat. So I'll give you a minute to do that so we can get our equation and our predictions. All right, so we said on this one here, this is the same example we used earlier with the babies. And so this was a linear, so I'm going to do my linear regression on this one. And of course, I'm going to copy it there so that I can use my equation. And so there's my equation. And so it says, using the model from example 1, what is the residual of the baby that is 5 weeks old? Interpret the meaning. All right, so at 5 weeks, alpha trace, we're going to do the 5 weeks. It is 4.47. So the predicted value is 4.47. Now at 5 weeks right here, the actual is 4.4. So it tells us to find the residual, and the residual is the actual minus the predicted. So I would do 4.4 minus 4.47. All right, so here we got the 4.4 minus 4.47 to get negative 0.07. So for the interpretation, the model overestimated. So when it comes out to be a negative value here, that's telling us that the predicted value is bigger than the actual value. So it overestimated it. If we had a positive value here, then our actual value would be bigger than our predicted value, and so it underestimated it. So when we interpret the data, that's what we're looking for there. So remember, you're looking at your table of values. You're really using everything you've learned so far by using it to find first differences, second differences, third differences. You are graphing it to see what kind of graphically it looks at. And just to show you that on the calculator as well. When you come to your calculator here, you can go and turn on the stat plot by highlighting that and hitting enter. And that will turn the stat plot on so that you can then see the points that you were graphing initially. So the points on my table are these points right here, and I could see that my linear model is a good model for this. So turning on the stat plot and seeing what that graph looks like, which we did up here, this was a quadratic model. That is a good way to look at which model to use, but you need to interpret that model, and then you're going to start doing the regression and then using that to predict information.